another link. Somehow it has worked. So we are thankful to God. We can the general aesthetics. And we had introduced the intravenous general aesthetics. Mainly, we had discussed on the barbiturates, and on the barbiturates, I did give a highlight on the structure of the barbiturates, what must be there, what must be intact. And we're going to mention again in the notes one or two things about the barbiturates. So we continue with the barbiturates, and we are saying it is only one category of the barbiturates that can be used as general anesthetics. And these are the ultra short acting barbiturates. Those are the only ones that can be used as general anesthetics. And because of their high lipid solubility, they penetrate the BBB very rapidly, get into the site, bring about the general anesthetic activity. And then, and there are some of them also that have sites that are highly susceptible to metabolism. So in addition to redistribution, they are also highly metabolized, and that also gives them much shorter duration of action. I think that's where we had started discussing the pentosodium. We have the pentosodium and methotrexate. Those will be good enough for as examples. Of the metabolism, but because of the redistribution. It is due to lowered concentration caused by redistribution of the drug from the brain to the blood. This is made possible because of the salt form of the drug. Of course, the high distribution first into the BBB, you give it as a salt, as I said yesterday. It has good dissolution in the blood. It can be able to equilibrate, give you high concentrations of the lipid soluble moiety. The lipid soluble moiety passes the BBB, gets into the brain, it has a very short duration of action. It does not have any direct toxic effects on the liver or kidney, although it crosses the placenta. Yesterday, we had mentioned that it can be used in pregnancy. Then we move on to the next one, and the next one is methotrexate. And you can see from the word that meth means there is a from hexane. It means it could also be having a six-membered group somewhere, and we'll be able to see that in its structure. And if we look at it, I think it's important that we look at its structure. Pentosodium. It has one of the nitrogen has been substituted with a methyl group, and we have said it's only one which can be substituted. Once you substitute this one, you cannot substitute the other one. If you do so, the molecule will lose activity. It will not be able to undergo ketoinototomic nature is necessary for these compounds to have even CNS activity. So therefore, that is the meth, that methyl group. We said on one of the nitrogens, you can have a small alkyl group, especially in most cases, it is a methyl group. And five, we said the 2 hydrogen in barbituric acid must be substituted with appropriate or long chain hydrocarbons. And if you look at this particular compound, you can see 5, 6, and that is where the hex is coming from. Meth hex, because these are 6 carbon atoms, and then you see the other one, unlike in methotrexate, this is an allyl group. So when you look at that compound, then we are saying these are 6 carbon atoms. When we looked at pentosodium, it had 7. But again, when you look at this compound, it has sites of metabolism. When you have multiple bonds, when you have number of carbon atoms and thiopentosodium, they belong to the same category because of the fact that this drug also can be rapidly metabolized. Now, when you have also double bonds or multiple bonds also increase lipid solubility. The fact that these three carbon atoms, although it has that area susceptible to metabolism, again, three carbon atoms, slightly increase in lipid solubility, but high susceptibility of metabolism, keeping these compounds others will be the same. Of course, for thiopenton sodium, this is an oxygen. So when you compare the basic ring, this is a normal barbiturate, the other one is a thiobarbiturate, and that is why also we need the compensation of the N-methyl group to further increase the lipid solubility so that this compound can be ultra characteristics of those area, those specific structure features. It has one nitrogen not substituted. It has to, for it to have CNS activity, groups at position number 5 must be substituted with hydrocarbons for starters. It doesn't matter which hydrocarbon, but there must be the two hydrogens at position number 5 must be substituted with hydrocarbons. So when we now come to methohexyl, we are saying it has the pentenyl group and it has the allyl group. Then we are talking about also to increase the lipid solubility. Again, it has an N-methyl group to further increase it as a general anesthetic. General properties of the anesthetic barbiturates, one of the very important properties of the general anesthetic barbiturates is that they must have very high lipid solubility. Must have very high lipid solubility. But again, although they have very high lipid solubility, they must be acidic. And if they are acidic, it means they have at some degree of hydrophilicity. So remember, for a drug to have activity, it must have some hydrophilicity. It must with their lipid solubility, rapid distribution and redistribution, as we have already mentioned. They have long side chain substitution, and you have seen for the group. For the methohexyl, it has the pentenyl group and it has the allyl group. So you can see they have long side chains, increasing their lipid solubility and hence the rate of passing through the blood-brain barrier. I think now it's very common when, of course, you have deportization. That's why we are saying there's an inverse correlation. It's not proportional. And higher the number of carbon atoms, the higher the lipid solubility. They have allowing it to be able to act as a general anesthetic barbiturate. Now we can if we want to mention some of the SANs, because as I said, the barbiturates are supposed to be studied in detail in the other unit, which we are calling the 2513, where you study and conversants, you study all those other. So I'll mention them briefly for the part that it's going to be repeated when you study the barbiturates. So structure activity relationship. And we are saying the barbituric acid, if you look at this is what we call the 1, 2, 3, 4, 5, 6. One of the factors or one of the structural features is that it has 2 nitrogens, and you can see those nitrogens are not substituted. Again, for it to be because of the lack of ability. It's highly acidic, but it does uric acid does not have any CNS activity, period. That is barbituric acid. There are 5 hydrocarbons, and the nature of those substituents, the nature of those substituents will influence the type of barbiturate you will have. Will it be an intermediate acting sedative like not these groups, and to a certain extent, also it can be dependent on the group, one of the group that you put on the nitrogen. That again we have discussed, and as I have said, we're also going to do it much later. Barbituric acid, we can talk about it as 2,4,6 trioxo hexahydropyrimidine. So in some of the books you call it 2,4,6 pyrimidine trione, 2,4,6 pyrimidine trione. So whichever way, so it's 2,4,6 trioxohexa hydropyrimidine. Does not possess any, that's barbituric acid. Acidic, remember, is hydrophilic. When you talk about acidic properties, you're talking about the hydrophilic properties of this drug. So it cannot be too acidic. If it is too acidic, like in barbituric acid, it is too hydrophilic. That cannot be. To make the drug sufficiently acidic, both one. To make the drug sufficiently lipophilic, the two hydrogen atoms at position 5, it will not have activity because quaternary compounds are charged and they will not pass through the control the concentration you require for it to bring activity. Like when you look at methohexto and you look at the penton sodium and compare with the others, for these ones, they are so potent that you might not even use, you cannot even use them as sedative hypnotics. You will use them as general aesthetics. Duration of action, again, we have said those groups in those areas will influence the lipid solubility, a function of the lipid solubility. So once you influence that substituent at position number 5, you will influence both the duration of action and the potency. When you talk about potency, remember the potency is the dose that is required to give a specific response. And we are only saying when you compare the barbiturate potent because of the group that is found at position number 5. Long chains are readily oxidized and thus produce short-acting barbiturate. When you look at the barbiturate, when you look at the ultra short-acting barbiturates, the redistribution is a main factor which controls the duration of action. But also the fact that their structure allows them to be rapidly metabolized, again, that also influences their duration of activity. Shortening further, we also have a factor, an influence on their duration of activity. Unsaturated analogs such as alkynes result in higher potency. So for these compounds, if you have unsaturation, areas of electron density, you find that these compounds have higher activity than the saturated analogs with the same number of carbon atoms. So when you look at methohexetol, they have brought in unsaturation. And when they bring in unsaturation, but unfortunately, the unsaturation, which increases lipid solubility, will also decrease. Increases lipid solubility will also decrease the duration of activity because it will increase the redistribution. Also, unsaturation will give us a site of metabolism. Compounds in unsaturation have sites of metabolism. They are liable to of activity, as we have said, because of three things. One, they are the long hydrocarbons, and because they are long hydrocarbons, there will be emission. Two, they are long hydrocarbons, and because they are long hydrocarbons are highly susceptible to metabolism, and then again giving us a short duration of action. If they are unsaturated by any chance, can result in these barbiturates having a very short duration of activity. But of course, as I have repeated again and again, has greater lipid solubility and depressant activity, but has shorter duration of activity. So again, branching increases lipid solubility. And even the branching must be at a certain point. When it is much nearer position 5, as we said yesterday, increases branching of the side chain, enhances activity. When it is closest to carbon 5, the resulting isomers are equipotent. So the isomers you get center. You can have the levo and dextro isomer. They are equipotent, but will influence the activity. And that is why both methohexyl, the position 5, so that you maximize on the lipid solubility. You increase the rate at which they pass the penetrate the BBB and their potency. So those factors are quite important. They are interlinked. The replacement of an oxygen atom with a sulfur atom, which we have said to give us a thiobarbiturates at carbon 2 position of the barbiturates significantly enhances lipid solubility. As that, the resulting modified versions of the barbiturates thus obtain a rapid onset of activity by virtue of the fact that they attain maximum barbiturate brain levels. Therefore, such drugs as thiopentasodium, rapidly acting, an advantage also, short duration of action, also have a quick recovery. And when you look at the structure of how 3, 4, if you are to name it as the way it's joined there, you can say it's 1, 2, 3, 4 butane, so methyl, and you can see if you have consider all the number of carbon atoms, you can say it's 1, 2, 3, 4, 5. It is a pentyl group, and then it has this other group there. That group is not unsaturated. It is just the ethyl group, giving us 7 carbon atoms. And yesterday I said for any compound to be atoms at position number 5 must be between 7 cars. Metabolism, even that one we had said, they are penton sodium. Because of that, thiol can undergo desulfuration to pentobarbital. All that has happened is that the sulfur has been replaced with oxygen. Now, when this happens, that sulfur increases lipid solubility. It changes, and then of course this barbiturate can still go further metabolism, and then it is removed from the body. So that we can say but of course, penton sodium barbiturate, it is not a general anesthetic. So desulfuration to pentobarbital, which is cleared from the body much more slowly than thiopentasodium. So we can mention the desulfuration, you give us pentobarbital, and then pentobarbital, because of the fact that it has these groups here, can go to type a number of metabolic processes. Remember, whenever you have an alkyl group, like these ones, free alkyl groups can be metabolized. So you can get omega minus 1 oxidation. Omega minus 1 oxidation comes to this carbon there, the penultimate or the ultimate. So you can get metabolism at the terminal carbon or omega carbon or omega minus 1 ultimate or penultimate carbon. And when that happens, this group there acquires a hydroxyl group. That is the secondary alcohol. That just gives you a secondary alcohol there. And of course, when you get a secondary alcohol there, remember now this becomes a chirostric. You can get enantiomas of the secondary, the dextroisomer, depending on the arrangement of the hydroxyl group. Is it alpha? Is it beta? So kindly remember the secondary alcohol metabolite can be enantiometric. Then you have omega oxidation. Omega oxidation is also this is what we are calling, and you can see, and this is an area I would want us to be careful, because I see many students making a mistake. And what they do is that when they come now to metabolize it, they forget this methyl group. They forget. I'm telling you, you get a 0. Because that does not become an OH. Because remember, this is a CH3. There we have a CH3. So when you metabolize it by oxidative hydroxylation, you must first of all put a CH2. And then you put your OH. So make sure that that basic principle sinks into your mind, because as even other compounds that you metabolize, you cannot destroy matter. It is only that the CH3 is converted to a methyl alcohol. So make sure you're very careful. So you can have mainly those two types of metabolism. There can be others that can happen. And of course, when again we study the barbiturates, we will mention any others. There can be cleavage. That barbiturate can cleave. It is an amide, it can cleave. But for now, because of processes, you will study them under the barbiturates. But it's important for us to note you can have omega minus 1 or the penultimate to give us a secondary alcohol, and that secondary alcohol then can undergo glucuronic conjugation to give us a metabolite that is highly water soluble, removed from the body. It can undergo omega oxidation, all the ultimate, and you can see this is a primary alcohol. That is a primary alcohol, and primary alcohols can go further to be metabolized into the carboxylic acid and aldehyde dehydrogenases to the carboxylic acid, or even them, they can be conjugated with glucuronic acid and removed from the body. So you can be able to get those as the main metabolic processes. But as I have said, the others, we will look at them when you will look at them when you're studying the barbiturates. But it's good to understand that anytime you have the alkyl group of oxidative hydroxylation catalyzed by cytochrome B450 enzyme. So this is just saying the alcoholic and carboxyl metabolites can be undergo glucuronic conjugation from the body. I doubt we need to look at this. We had already looked at. I only brought it so that you remind us yourselves. Barbiturates. I do not need to go again. We had already discussed it in detail. Then we look at metabolism of methohexitol, understand, and the pentenyl group. This is the pentenyl group. Has a triple bond. And in addition to the triple bond, this is the carbon which has hydrogen. That carbon is called the allelic. Next one is the one which is on the inside. It cannot undergo metabolism very easily. But if it had continued from here, it continues, then this would be the allelic carbon atom. So when you have an allelic carbon atom, the allelic carbon atom is it's one of the highly susceptible carbons in terms of metabolism. So this carbon here in methyl is the allelic carbon atom, and that is one carbon that can undergo very rapid metabolism. So this compound can very easily be metabolized in two ways. One, it has that allelic carbon atom, which can undergo hydroxylation, that one there. It oxidative hydroxylation. There are other ways which will give you minor products. Like you can see, this is a double multiple bond. You can get epoxide formation and formation of the diols. But I want us just to major on the main metabolic processes or the major metabolites in the blood or that are found in the urine on excretion, and they will be either the conjugate of the penultimate metabolite or the conjugate of the allelic conjugate, the conjugate of the allelic hydroxyl metabolite. So those acts on their own, you will mention all the others. Of course, also, you can see this group there. So this also can be another route of metabolism, oxidative and dealkylation. So indeed, actually, the main route of metabolism can be this one and this allelic one. And those are the major metabolites that you find. Metabolism occurs in the liver. And you see, these drugs must get into the brain. And almost all barbiturates, you find that they have what we call fast pass metabolism. They can be metabolized in the liver before they get into the site of action, so that fast pass metabolism can also have an influence on their activity or their concentration. Metabolism occurs in the liver through demethylation and allelic oxidation. Side chain oxidation is the most important of the biologic activity. So the drug, this one, we can call it N-methyl 5 position there. Allele is that group there, allele. Then 1 prime, we are saying 1 prime because again, we must number this group and we are numbering it as from there. 1 prime, this position 2 prime, position 3 prime, position 4 prime, position 5 prime. Discussed carries position 1, carries position 2, carries position 2, should be position 1, position 1 carries position 2, carries position 3, 4, just to think them out, get them from the call structure is why we are putting a prime. So when we look at this structure, I just wanted us to understand why we are giving it that name. N-methyl for that. 5 is this position there, 5. Allele group is this group there, that is called allele. CH, when you have that CH2, CH2, that is what we call the allele group. 5 N-methyl 5 allele, and then again at position number 5, which is that position 2 prime, 3 prime, 4 prime, 5 prime. So you have 1 prime methyl 2 prime pentenyl, that one there, the double bond, multiple bond starts. So 2 prime pentenyl barbituric acid. So I hope you can be able to see. We only need to name the structure for us to give it its UPAC name. Is metabolized. Sorry. It's metabolized to the N-methyl 5-valent. So up to there you can see the same, quoting the same. Now it is only here where you have the 4 prime hydroxyl. And if you ask yourself 4 prime again, that is position 1 prime, 2 prime, 3 prime, 4 prime. And you can see your 4 prime is the allylic carbonatom. 4 prime hydroxyl, 2 pentenyl. Everything else remains barbituric acid. This is hydroxylation of the penultimate. So that is the major hydroxyl group. And because silic acid, it can be conjugated and the compound can be removed from the body. Once conjugation occurs, as we have said earlier, the compound has very high water solubility. Even as it is, a bit of it can also be removed from the body. So I hope that even the name 5-allyl, 5-allyl, 5,1-methyl, 2-pentenyl barbituric acid. So those are the two main. As I have said, and I repeat again, they are not the only metabolic routes, because I've said these compounds can even undergo cleavage. They can undergo cleavage and so on. But we are looking at the main metabolic pathways which will result in termination of the biological activity. Once you terminate the biological activity, the other one is now to conjugate and the compound is removed from the body. So I think that with that, we are done with the general anesthetics. Has to start the centrally acting muscle relaxant. So let's see the question. 61. Can we move on? Yeah, I'm doing well. When we do now the central reacting muscle relaxants, only one small topic. Because again, as I said, this one is not a broad topic. In fact, it were not for the challenge I got, we should have almost finished. But anyway, all is well. All that ends well is good, and we thank God for everything. So now we start with the centrally acting muscle relaxants. I do not know whether you have studied the peripherally acting, the ones that affect the neuromuscular junction. The muscle on the neuromuscular junction. That is not us now. We are not looking at those ones. We are looking at the ones supposed to be CNS 1, and therefore you're looking at those drugs that again must pass the BBB, get into the brain, get their own receptors, as we have talked about all the other drugs, general anesthetics, all of them. Yeah. Sorry. Just 1 little minute. Sorry about that. So we are looking at the centrally acting muscle relaxants, and I've just said you can have the centrally acting or spasmolytics. Models, I don't teach those ones, but I will do the centrally acting again. Central acting muscle relaxation. They will have an influence on the tone of the muscle and help you in case you have pain. For pain, there is spasms, then they will help in that. Central acting muscle relaxant is a drug which affects skeletal muscle function and decreases the muscle tone. It may be used to alleviate symptoms such as muscle spasms, sprains, and even pain. Muscle relaxants are classified into two major therapeutic groups. You have the neuromuscular junction blockers or neuromuscular blockers, and those ones you do them elsewhere. And then you have the spasmolytics, and then spasmolytics are the ones we have an interest in. They are the central acting muscle relaxants. Indications, of course, as you can see, they can be used for muscle spasms, sprains, and pain. Indications: spasmolytics are used to alleviate musculoskeletal pain, spasms, and to reduce spasticity in a variety of neurological conditions. The only difference is that they're acting from the mind. They must, they must have good lipid solubility, go through the BBB, get into the brain, and block the receptors within the brain. That is the only difference. So when you look out also at the spasmolytics, we are looking at the ones which are centrally acting, the ones which are direct action, and miscellaneous. But the ones as we want are the ones which are centrally acting. Once kawaida yetu, so that it gets into our mind. Either enhancing the level of inhibition, casting the GAs, they enhance the level of inhibition by binding an allosteric site, and by is what we discussed, or reducing the level of excitation. Even though that is not new, we have talked about the aspartate, and we have also talked about AMPA, and we have said these are the main excitatory receptors that use glutamate or glycine. These receptors, you block the level of excitation. So again, nothing really new. Inhibition is enhanced by mimicking or enhancing the actions of endogenous inhibitory neurotransmitter like GABA. You already know GABA, gamma aminobutyric acid. You've already mentioned it. GABA is the chief inhibitory neurotransmitter in the mammalian CNS. So you can see how we are building nothing really much. In humans, GABA is directly responsible for regulation also of muscle tone. So once you enhance the activity of GABA, it is inhibitory, then you will decrease the muscle tone. Centrally acting muscle reactants reduce rigidity of the muscles without affecting consciousness and normal voluntary movements. So when you take them, you will be able to do all your other jobs, walk and what have you. But the pain can be used in in poisoning conversions and various, as we have said, various spastic disorders or various pains in the brain. That is very important. Effectively decreasing the skeletal muscle tones and involuntary movement. You can see we have said the voluntary movement. The voluntary movement is the one which you move with involuntary movement. Examples include mefenecine, methocarbamol, carisoprodol, cyclobenzaprine, and diazepam. So we will look at a number of examples, of course, just as we have said before. done before by them, we are able to understand their structure more. Of course, for us, the main interest is to be able to put them in their specific structure classes. So still structurally, centrally acting, muscle relaxants, as we already mentioned, they reduce the skeletal muscle tone and are used for in treatment of various things. We've already mentioned muscle spasms of local origin, such as strains, sprains, and lumbago, spasticity and spasms. Also relieve pain and spasm associated with that. Drugs targeting, already we have said, we can have the drugs targeting dopamine or GABA systems can be used to modulate muscle relaxation. And remember, so we are saying you can give either drugs related to dopamine or dopaminergic drugs, or you can give a drug that have an influence on the GABA system. Because remember, when we were discussing Parkinsonism, we say dopamine is important for relaxation. So it decreases the muscle tone. Acetylcholine is important for the contraction. It increases the muscle tone. So therefore, you can either influence dopamine or you can influence GABA for you to have decreased. Dopaminergic drugs like those used in Parkinson's disease help restore balance between dopamine and acetylcholine. We have mentioned the basal ganglia, improving motor control and reducing muscle rigidity. We have already discussed that. That's not news. GABAergic drugs such as benzodiazepines, which we are going to mention, and all those others. There are many. Enhance GABA activity and anesthetic sites within the GABA receptor, GABA A receptor, increasing or enhancing or potentiating GABA activity, and therefore improving or promoting cyclobenzaprine. We have mentioned them. I think this was just a repeat. Carisoprodol, methocarbamol, so again, to be able to classify them in their specific and able to discuss them individually. I don't know why I repeated this, but we have already mentioned this. They act as muscle impulse transmission in the interneuronal, selective action on the cerebrospinal axis. They depress the spinal and supraspinal reflexes of the muscle tone. This is a lot of pharmacology and so on. So no effect on the neuromuscular junction, but reduce upper motor neuron spasticity and hyperflexia. So they do not have any influence on the category is the glycerol monoethers derivatives. Glycerol monoethers and derivatives. And this formate and methocarbamol. So those are some of the ones you discussed. Alkane diodes. You can see this alkane diode. It means there is an alkane. It might not just be ending the hydroxyl group. It could be an alkane, and then there is a hydroxyl group connected to another group, an oxygen connected to another group. That's why we are calling them alkane diodes. So we have the alkane diodes and derivative. Alkane diodes, we are going to discuss them. And then under that, we look at meprobamate. Meprobamate is not very strong, but it has been derivatized into other drugs like meprobamate. But if you look at meprobamate, we look at carisoprodol and metaxolone. Under the benzodiazepine, and razepam. You look at three drugs under the benzodiazepines, which just relax the muscles, increase the muscle tones, and then you have the clozoxazone. Again, if you look, even when you go out there for the 4 ones, for the 5 ones, you've already been out there. I hope you are able to see some over-the-counter drugs that also contain. They are painkillers. They are painkillers, like you could have a drug containing paracetamol and clozoxazone. The clozoxazone, the advantage is it relaxes the muscle. So it is specific for somebody who has a sprain, who has muscle pain. They will relax the muscles, but they'll still be able to move. They does not affect their movement because you have said it mainly you find it in quite a number of the over-the-counter drugs. Then we have the GABA receptor agonists, do what GABA does. And then we have an example is baclofen. So we expect baclofen to have a structural similarity to GABA. Then we have the TCS. TCS stands for tricyclic antidepressants. That's the TCA. Tricyclic antidepressants are fused to each other. And most of the tricyclics are used as that we'll discuss there, and that is cyclobenzaprine. So we'll be able to quickly to go through those structures or those compounds or those classes. As I've said, the biggest advantage is that these ones are not as huge as the narcotic and calling glycerol monoethers. And this is a structure of glycerol. So you can see, you can start from in structure for it to be glycerol monoether. We expect it to have this basic structure somewhere. So you can see there is a CH2OH joined to a CH like prototype. We can start from there, and you can see CH2OH there. Then we move on. We go to the CH. You can see the CH2O, and that is why we are calling them glycerol monoethers, because you find that the last hydroxyl group, and because it's only one, not two, that's why we are calling them monoethers. So you can understand where the name comes from. It's from glycerol. So we are considering the glycerol has been replaced in most of them with a phenyl, substituted phenyl group with increase in activity. Glycerol might not have any activity, but once the glycerol is substituted with a substituted phenyl group, then you have a muscle relaxant activity. So that is mefenacine. You can note it has methyl group at position number 2. So if you look at it, we can call that structure there is toluene. Toluene. So you see at times you and I think we mentioned this when you were also looking at the COMT. So and then you can see now it is just toluene glycerol. That is all that is. If you look at clofenicin, it has a slight difference. In mefenacine, it has a meta. Sorry, an methyl group. In clofenicin, it has a parachloro group. We know parachloro group or a group parachloro group will block the site of oxidative hydroxylation of the phenyl ring. And we know also the activity. Again, so that's one difference between mefenacine and clofenicin. Clofenicin, the chloro group, it's at para position, at the position where it blocks the hydroxyl the oxidative hydroxymetabolism of the benzene ring. Number 2, if you look at chlorphenzene, this is a hydroxyl group. This is an amide. If you look at that, that is also a difference that indeed, in the mefenacine in chlorphenzene has also undergone carbamylation. And this carbamate formation or generation of a carbamate is very important because it stabilizes that compound. Remember, this amide is stabilized by resonance. So the carbamate is more stable to metabolism. It has also slightly lower, it has also slightly higher lipid solubility compared to the alcohol. Stabilizes that molecule, gives it a much better muscle relaxant activity, and also the parachloro group also improves the activity. Methocarbamol, again, just like chlorphenzene, there is carbamylation, and at the same time, we compare mefenacine. It is a slightly, it is a derivative of it's a structural analog of mefenacine, where the methoxy group has been replaced at the same position, the methyl group, and again there's carbamylation. As you see, the position is muscle relaxant activity. So those are the main groups, and by now you are able to look at the structures. And I hope when you look at a structure, now you can say something. You can compare why that chloro group at para position. There's a methoxy group there because there's a site of metabolism, but nevertheless, it was found to increase the activity. Position 1, position 2, position 3. Because we say it's a molecule, it's a parent molecule when we number this, when we do pack system. So we can say at position 3. So we are starting that 3 stands for this position 3. You have a 2-methyl, position 1, position 2. So 2-methyl phenoxy. So we are starting from there. 2-methyl phenoxy, that is a substituent. 2-methyl phenoxy is a substituent. So 2-methyl phenoxy, 2-propanediol, 1, 2, 3. 1, 2-propanediol. So that's where the name has come from. You've already done a lot of, I believe you did a lot of UPAC. I hope you did. The naming of this compound, they had organic chemistry they did. So the lecturer was a bit disappointed. But anything that is UPAC name and we are saying it's reduces a reduction in spasticity. It has been observed to block both inward sodium and inward calcium currents. Remember, we did mention that they can either inhibit the excitatory receptor. The excitatory receptor is the one which is responsible for calcium and sodium. They can enhance the GABA inhibitory. We have already mentioned all that. So synthesis, again, remember that start with those with that carboxylic acid derivative. They always take number 1. In other words, if we had a carboxylic substituent here, the parent compound, we would have considered it to be a carboxylic acid. So there is that priority, which I hope you can also remember. So when we compare the hydroxyl group and the methyl group, and that is why we are naming this compound as a product of the phenol, because the hydroxyl group is given first priority. So we look at this compound as a phenol, and then now name or now give it all the other substituents. So that is position 1, position 2, 2-methyl phenol, and then 3 chloropropane, that is easy 1,2-diol, and again that is a halogen, that is a nuclear delta positive. This is nucleophilic attack, and the chloro group disappears, and indeed you get your methanothene. Activation of O-creso, that's also that is the trivial name for that compound, O-creso or 2-methyl phenol with 3 chloropropane 1,2-diol affords methanothene, as we have seen. Metabolism. And incidentally, this compound, the higher metabolic product, the toluene, and that's why I said about toluene there. Lactic acid, which is inactive, methanothene carbamate. If you are to clear from here and then you put C double bond O, we have said that you put an amino group, that's the carbamate. If you action and sustained relief, making it preferred choice in clinical practice. So you can carbamylate the methanothene, and we have seen also the chlorphenathene is also carbamylated. The only thing, when you collect the carbamate is stabilized through resonance. It has higher lipid solubility. It is therefore more metabolically stable. It has higher lipid solubility, gives you slightly higher concentrations, and therefore better activity. So we are saying that is a product. You can see all that has happened again. You must remember you have to start from there. This is the CH2OH. It becomes a carboxylic acid. So this becomes C double bond O and then OH. And so therefore you remember that you be one carbon less. So do not again put this one. So this will be our first one. And that is why that's C double bond O and so on. So you get the methanothene toluene lactic acid derivative. So you can give this one drug, and because of this structure, it will undergo a lot of 6 times per day as per requirement. Again, because of its high water solubility. Because of the fact that it's a primary alcohol, it can undergo a lot of bypass metabolism, and therefore that is why you're giving a lot of it, and then it's rapidly metabolized administration. Again, that area is the area mainly. Now we go to the next one, chlorphenathene, and we did say when you look at chlorphenathene, 2 differences: para-chloro group has much higher activity. Again, here you are starting the other one, we are starting with O-creso, but now you're grouping the same compound we condensed when we were making methanothene, and then you use phosgene of 4 chlorophenol with 3 chloropropane 1,2-diol, followed by reaction with phosgene and ammonia with loss of hydrogen chloride affords chlorphenathene carbamex. The simple, very simple ways of is weakly active and short-lived, as you've already mentioned, a very short to the carboxylic group catalyzed by alcohol and aldehyde dehydrogenase. So you can't behind and then aldehyde dehydrogenase for weakly active. Carbamylation, as we have said, can decrease the activity. We've already seen that. Then also parachlorination, as in chlorphenicin, increases the lipophilicity, although we have not said that chlorphenicin, or not methanosin, can undergo oxidative hydroxylation. That is another route of metabolism from what we have discussed all along. So the parahydroxylation can also happen in methanosin. So when you look at chlorphenicin, you have blocked that position because remember when you look at metabolism, it's only that some are major routes of metabolism and others are minor. But ultimately, all of them result in reduction of the amount of the drug that you had initially given. So parachlorination increases the lipophilicity. We had already mentioned halogens increase lipophilicity. And also it's again also halogens are electron withdrawers. And because they're electron withdrawers, they also decrease the rate of hydroxylation of the benzene ring. So they are doing three things. They are halogen, they are electron withdrawers. So they withdraw electrons and further, so they decrease the reactivity of the benzene ring to oxidative hydroxylation. Number three, they increase the lipid solubility. So the halogens when you see them block the position for metabolism, find the lipid solubility, and therefore the compound can penetrate the lipid membranes, be it in a GIT concentration, however, still fairly rapid. That is for the for even the chlorphenicin and involves glucuronidation of the secondary hydroxyl group. So if you look at chlorphenicin, it is used to diminish skeletal muscle spasm, as we have mentioned, resulting from osteoarthritis is quite high, 800 milligrams thrice daily, reduced to 400 milligrams 4 times daily or less as required. But you can see the dosage is slightly lower than that of methanosin. Mechanism, we have already mentioned this mechanism of action of the glycerol monoethers. Of course, we have talked about. So the glycerol monoethers can enhance activation of the GABA receptors, increase chloride ion influx. These are things we have excitability. This actually helps to decrease muscle tone and induce muscle relaxation. But they can potentiate the GABA activity and therefore increase, can potentiate GABA activity and hence increase the inhibitory activity of to release GABA. Some glycerol monoether may facilitate the inhibitory activity within the CNS. So these are things, so they have agonism so that they can bind. When you talk about agonism, it means they can bind the GABA. And also glycerin receptor modulation. Remember, I have told you that GABA, when you talk about these receptors, the glycerin is also a core agonist. The glycerin is also a co-agonist. So these they can also bring about glycerin receptor modulation, so they can have glycine agonism. Glycerol monoethers may also act on the glycine receptors, which are inhibitory also receptors in the spinal cord and in the brainstem. Action Activation of the glycine receptors can lead to an influx of chloride ions into neurons, similar to GABA A receptors, resulting again in the same. Also, the GABA release, all of it actually is potentiation of the inhibitory neurotransmission. And once you inhibit the chloride, the muscles, and once you depress the muscles, there will be there will be relaxation. Another one, inhibition base, the NMDA receptors, glutamate receptor antagonism. Some glycerol ethers may exhibit antagonistic effect on the excitatory glutamate receptors, such as NMDA. We have mentioned the net increase of muscle tone and therefore relaxation. Central nervous system, also depression, direct sedative effect. So they can bring about also sedation by enhancing inhibitory neurotransmission. General CNS depressant effect. This can result in sedation, reduced muscle tone, and overall muscle relaxation. Again, a lot of interrelation. Activity of spinal reflexes, which play a role in maintaining muscle tone. By dampening these reflexes, the compounds also help in muscle relaxation. But the most important is for us to note their role in inhibition of the excitatory transmission and also the enhanced, so all the others are falling in place. All this we have done, we have spoken mefenacin, just a low and basis on exaggerated reflex activity, can control it, and therefore it can be used in some of the psychotic states available in tablets and also in types of tremor, together with the antiparkinsonian drugs that I mentioned. That activity. The side effect is weakness, because again, remember, it's causing muscle relaxation. You feel weak, although they are not having a much activity and they are not influencing the voluntary muscle activity. They will definitely, to a certain extent, and therefore you have muscle weakness, you have nystagmus, which is eyeball movement, you can have double vision and muscular incoordination, because they're actually affecting the muscles. Common side effects, because also of the other drugs. So we are done with mefenacin. I think we are done with chlorphenazine. Then we go to the other, methocarbamol. Methocarbamol, again, very similar to mefenacin. It's only that, as we have said, it has a methoxy group there. Mefenacin has a methyl group, and then this group that is carbamylated, whereas mefenacin is a hydroxy group. Again, very similar. Group enhancing its pharmacological properties, because we have said this metabolism through resonance decreases water solubility and therefore enhances lipid solubility and therefore higher concentrations. Similar to chlorphenazine, carbamate, of course, 2-methoxyphenol as a starting material. So what you will be changing is the starting material, because this time you do not want a methyl group, you want the same compound followed by you to do the carbamylation with also hydrogen chloride, a 4th methocarbamol. So when you talk about the carbamate, you will use the phosgene and ammonia, but for the others, you will not. Methocarbamol is metabolized in the liver by dealkylation and hydroxylation. When we talk about it as this, so it can undergo oxidative or dealkylation. Oxidative or dealkylation, and of course also, because you see now, this has been stabilized. I want to believe the kind of hydroxylation that might happen is on the phenyl ring, and we have this and that. This can have also metapara. So you can, that's what you're saying. Several metabolites, you can get hydroxylation at that point. You can also get at hydroxylation of that at that point. So those are the main metabolites again, because dependent on the structure. Oxidative or dealkylation. The others did not have an alkoxy group. This one has an alkoxy group, so that can allow for oxidative dealkylation. And then the carbamate has been stabilized and therefore not readily undergoing metabolism. Methocarbamol, again, of course, it's a CNS depressant. It's traditionally suggested for use in acute painful musculoskeletal conditions such as muscle tension and pains, just like the others, as we have mentioned. Muscle relaxation is because of its sedative action. Drowsiness, dizziness, and lightheadedness are common side effects because it's causing also sedation. So again, very similar ones, very similar to the others. What are it used? It can also be used in conjunction with the other drugs we have discussed in Parkinsonism and also in cerebral vascular mischief. So in pains, and as adjunct, I think as an adjunct, yes, as an adjunct in the management of Parkinsonism. Yeah, problem is here, and I think that's why we didn't concentrate with it. These muscle relaxants is that they also bring in muscle weakness. This person already cannot control their muscles, so it has to be, there must be very good management for you to be able to use these drugs, because they're also having, as we have said, remember, and already the person who has Parkinson's already is having a problem. So even though they can be used, they can just use an adjunct or added, it can be added, but the prescriber or the physician must be very careful, because so that they do not worsen the muscle coordination. Structure activity relationship of the glycerol derivatives, and we've already mentioned it. This is just a summary, and we are saying substitution of a small alkyl or alkoxy. We talked about the small alkoxy. Also, we have mentioned in methocarbamol. Again, in the saying substitution of a small alkyl or alkoxy group increases activity, and we have examples of mefenecine and methocarbamol. And I'd expect, and you mention, if you do this happens. You're talking about the whole group. It is good to give the example and draw the structure to show that you understand what you're talking about. The other substituted benzene derivatives are generally more potent than the corresponding para or meta isomer, and therefore you have mefenecine, methocarbamol. That's when we are looking at the alkyl and alkoxy. When we are talking about alkyl and alkoxy, it is better when you put those groups in other position rather than meta or para. But when you talk about halogens, it's better when you put the group at the para position. Is referring, it's an addition, is a continuation of that one. Again, carbamylation of the secondary terminal alcohol increases activity. Terminal alcohol increases activity. chlorphenesin and carbamate and methocarbamol. So again, we have already mentioned that stabilization by resonance. You have an increase in lipid chlorination, increases the lipophilicity, and seals off the para position from hydroxylation. We have chlorphenesin, carbamate, and again we can also add the point there, which we added the third point, that of course the halogen also decreases the rate of hydroxylation of that compound. Not only does it block the position that they are electron withdrawers, as I already mentioned. Substitution on the benzene ring with the hydroxyl group, amino group, or an acetyl group decreases activity. So you cannot put a hydroxyl group, you cannot put an amino group, you cannot put an acetyl group. Those will decrease activity. The groups that are accepted is methoxy group. You can have a halogen or a methyl group, and the specific and have indicated the necessary positions for those compounds to have good activity. And that finishes the glycerol ethers. Do you have any question? Yeah. Until you become dry. Then now we move to the next one, which is substituted alkane diols and their derivatives. And you can this is the diol, this is the alkane area, all that. And we have carisoprodol. We have the carisoprodol. And we are only considering this area here. This alkane there, and then you have the oxygen there, and the other oxygen there. You can see this is an oxygen. Sorry, let me see it clearly. No, it's an oxazole ring because you can see the nitrogen and oxygen are separated by. It's a derivative, not an oxazole. It's a derivative of an oxazole ring because again, an oxazole ring bond there, so we can't say it's a derivative of an oxazolidine because of the unsaturation. But we can see of importance, it still fits in the alkane diols. We are just looking, and then you have meprobamate. Again, meprobamate, you can see the whole of this section there. Section there. And if I think we can be able to compare it, carisoprodol. Isopropyl group there, and there is meprobamate. Group will increase, not very, it's also block the amino group, which makes the compound a little bit more hydrophilic. So that group there is helping to improve on the lipid solubility of that compound. And then when we come to this area by resonance from metabolism, so you have increased lipid area, lipid solubility. It is stabilized with resonance solubility compared to meclobamate. So those, I think, are the main compound metaxalone can. Again, they selectively depress the spinal and supraspinal polysynaptic reflexes, involve the regulation of structural change to carisoprodol, and carisoprodol, as you can see, it's the N-isopropyl derivative, proper derivatized, metabolized to meclobamate. It has 2 chiral centers and formulated as a racemic mixture. You can just look through this. This is the way it can metabolize until you get your carisoprodol. Precautions and contraindications. It can cause sedation, just like the other, to cause significant, because it is more, you have put an alkyl group, it has higher lipid solubility. To get into the brain in high concentration, affect the ability to perform abuse. This is one other problem. Prolonged use can lead to physical dependence and withdrawal symptoms. Carisoprodol has a potential for abuse. Combination with other CNS depressants. The cytochrome 219, genetic variability. Patients with genetic variation metabolize carisoprodol differently, either leading to increased and they can have an influence on the concentration of the carisoprodol. That is not new. So nothing new there. So sedation, dependence, and then also there can be genetic variability. Pregnancy and lactation, the safety of carisoprodol during pregnancy, lactation has not been established. It should be used only if the potential benefit justifies. No, because you have other drugs. So that are some of the challenges we have talked about. It can cause diazepine, opioids, others, depression. And we have already talked about the 15. So if you have cytochrome 2C19 inhibitors, drug medications that inhibit cytochrome 2C19 can increase carisoprodol plasma levels, leading to enhanced effect and potential toxicity. Drugs like together. Again, these are so that these users medications that induce the cytochrome its efficacy. Drugs like okay, you'll be studying, for those who have studied the other unit, you have studied carbamazepine, you have studied phenytoin, phenobarbital, and rifampicin. Is an anti-TB drug, which we've already looked at. The isoenzyme, genetic polymorphism or genetic induced. So this doesn't comparative effectiveness compared to what we'll be looking at later. It is noted for long-term use. So those are some of the very important things to note. So that even sometimes formed, like if you see somebody coming for such a drug, you are informed and you know. If they come more than once, note. Is because they have looked at its advantages and also its disadvantages. Then we go to metaxalone. Again, metaxalone, that is a simple structure. Derivative because of that oxazole ring there. It is fact that an alkyl group is not that oxygen and this, it is still an alkane diol. It fits in that group of the alkane diols. Again, remember, CNS receptors of those found that drugs that bind the neurons or bind the nerves, somehow they can have very different structures and still bring about the activity. Metaxalone is used with rest, physical therapy, and other measures to relax muscle tones, but only that, so just like the others. So a patient can be advised to rest, to have physical therapy, and also to take the drug as to improve on the muscle pain. It is metabolized by cytochrome. Position 5,3,5 dimethyl phenoxymethyl 2 oxazolidine, oxazolidinone, and you're saying oxazolidine because the oxazole ring, it's not an oxazole ring, because when you talk about the oxazole ring is when you have an oxygen, you skip one, you have a nitrogen, and then there is double bonds. For you to call it an oxazole, it has to have the double bonds. So now when you remove the double bonds and you still have an oxygen and nitrogen, then we call it the oxazolidine. Now in this one, for you to do so, there is also something else that has been done. There is double bond. So that is how the name coming about. Known ring with a 3,5-dimethyl phenoxy substituent. Key chemical features, of course, you have the oxazolidinone ring. The oxazolidinone ring is a 5-membered lactam structure. Again, remember we had mentioned lactam. It's a 5-membered. A lactam is a 5-membered. Talk about a lactam. So remember, but you see the lactams that we were used to were 4-membered. Beta lactams were 4-membered. So a lactam, as long as it's a cyclic amide, it can still be a lactam. So this is a 5-membered lactam structure containing one nitrogen. They are separated. The oxygen and nitrogen are separated by a carbon. That is why it's an octazole. This ring structure is crucial for the drug pharmacological activity. So that oxazolidine ring, the 5-membered lactam structure containing one nitrogen and oxygen in the 5-dimethyl phenoxy group, the presence of the C5-dimethyl phenoxy group linked to the drugs lipophilicity and its ability to cross the blood-brain barrier. That's exactly in the central muscle relaxant axis. So again, we are saying the phenyl group and the methylene bridge is important for its activity, giving this compound the lipid them again by reducing the firing of neurons by causing muscle that cause muscle contractions. Again, we have looked at all those inhibitory methods in which decrease muscle contractions. Pharmacokinetics, absorption, it is well absorbed from GIT. However, its bioavailability can be influenced by food intake with a high fat meal, significantly increasing the drug plasma levels. When you have give a high fat meal, you're increasing the lipid solubility, and therefore the drug can go into more, can go more into that environment, can dissolve in the lipid absorption. That distribution is distributed throughout the body, and its lipophilic allows it to cross the blood-brain barrier. We have talked about its phenyl group, its methylene bridge, important for its lipid transport. The drug is extensively metabolized in the liver, the metabolic pathway involving oxidation, dealkylation, and conjugation reactions, which are catalyzed by cytochrome P450, particularly cytochrome 182, cytochrome 2D6 are involved in its metabolism. Sometimes you cannot really remember all the specific, be a lot to remember each of them. But all we are saying is that cytochrome P450, you can see it has the methyl groups, and those methyl groups to me are similar. So, and those methyl groups can undergo oxidative hydroxylation characterized by cytochrome P450. So that they can undergo oxidative hydroxylation characterized by cytochrome P450. When you look at this compound, we said it has a methylene bridge, which is joined to the oxygen. Again, this methylene bridge all dealkylation. Active to happen allows for oxidative all dealkylation. That group going there, and that group going on. So I want to believe the majority, the main metabolism, oxidative hydroxylation and oxidative and dealkylation are some of the important metabolic processes. And I've also shown you, and I think that's what we have said, but they involve oxidation and dealkylation. Those are the main. And usually when you do oxidation, again, you get the hydroxyl metabolite. The hydroxyl metabolite has now the functional group. It can readily undergo conjugation. Once it undergoes conjugation, very high water solubility, readily removed from the body. Taxolone and metabolite are primarily excreted in urine. The drug has a relatively short half-life, setting multiple dose throughout the day. Half-life is because of the rapid metabolism. Again, whenever you have any group, the natural group, especially attached to an aromatic ring, it undergoes short duration of action. Are you having another lesson? Uko na lesson ingine? I like it's already it's 4:15. We started at 4:15. We started a bit late. If you continue, you're okay there. You give another one lesson or two and another 1.5 lessons, we should be done, I think. Maximum, I think 2 lessons, we should be done. Benzazos and the We continue to force that. Thank you. Anybody else of the same opinion? So let's continue a bit. So we are now done with. We were on metaxalone, and now we are done with the alkane diols. One example, the benzazoles, benzazole, and in this one you have the clozoxazone. And as I said, clozoxazone is a drug of the analgesics, which at times are given as over-the-counter drugs. So it's a member of the class of 1,3 benzoxazoles. Benzoxazoles, so again, very similar to the metaxalone. It has an octazole ring. The other one had an octazolidine ring. That is 1,3 benzoxazole 2-on, in which the hydrogen atom at difference between this and the other structure. The other one, the octazole, the octazolidine ring was on its own. It was not fused. There was indeed a benzene ring, but they were not fused together. They were separated. You can see there was a benzene ring and there was the octazole ring, the octazolidine ring. They were joined through a methylene, but they were not fused. But the two structures were there. Now, when we look, my two rings are fused together. So let us note that yes, the two rings are the exact structures there, whereby we are talking about it's a benzo octazole. It's a benz octazole because of the fusion. And at position 5, of course, that is heteroatom. So we start with number 1, and then we make sure the other heteroatoms and the other subsequent of the 5. So at position number 5 of the with a chloro group again to improve on the activity. So that is the structure. This actually is the structure of clozoxazone. It is metabolized again for metabolism. This is the group, the position group most probably is because of this group. This ring. If you look at this oxygen to increase the metabolism, this, although the position for this oxygen, it will decrease most of this ring. The position it would increase most is ortho meta para position. That is also an ortho. It's an ortho para director, but it deactivates the ring. But although it deactivates the ring, it's also a para ortho director. So this position seems to be the most most susceptible to oxidative hydroxylation because of the substituents that you have. Para-6, this would have also directed the oxidation of the number ortho meta para oxidation because that already has another group. Then the chloropara director. So it will also direct to that position. So position 6 seems to be the most active or the most active position of oxazone. We do get that product. Metabolized by carbon hydroxylation, position 6 hydroxylation, again catalyzed by cytochrome P450 enzymes. As I say, this is sometimes very difficult to remember which isoenzyme. It is rapidly metabolized in the liver and excreted in the urine, primarily as conjugated form of glucuronide. The minute it is hydroxylated, the hydroxyl group will be conjugated and the compound will be removed from the body. How is it synthesized? 2-amino 4-chlorophenol. Again, all these compound, the amino, I said last time, still name will be the phenol, and then position 1, 2, 3, 4, position 1, 2, 3, 4. So both positions are the same. So position 1, so 2-amino 4-chlorophenol. And then you use phosgene. Actually, it is heterocyclization. An N, all we are doing is all the first gene. This is usually use both highly electron in the drawer. So this attacks this position with dehalogenation, and that results in, that's what you're calling heterocyclization to get the oxazone. SAR, the benzene ring, the benzene provides a planar and stable structure. Most of these compounds indeed they do have a significant structure, and we have seen like the chloro group. And we know what the chloro group does. The chloro group, like ortho meta para, it has indeed blocked the one of the sites of metabolism catalyzed by the oxygen, but more so it is an electron withdrawer and therefore an electron a ring deactivator. At the same time, it also increases lipid solubility, and I think we have discussed that at length. So therefore, the substitution is very, very important, and it was found that the halogens were responsible for the best in terms of pharmacokinetic absorption and so on. They increase halogens, increase lipid solubility, and also the pharmacodynamics of the molecule. Remember, even the chloro groups or the halogens have lone pairs of electrons, influence on the electronic nature of this molecule. And you can find that this group is able to interact with the receptor because of that substituent. And that is why we are talking about the pharmacodynamic. Also, that halogen is an electron withdrawer. And because it's an electron withdrawer, it influences this ring in terms of electron density. And therefore, it can influence the binding of the resultant ring with the receptor because of what it is doing, but through electrons. The way pharmacodynamics, remember, metabolized. Halogen substitution, the presence of halogen, like chlorine, at the para position is essential. The chlorine atom at the 4th position, para position, yes. So that halogen, very, very important. And as I have said, it can also influence the binding to the receptor. It can have also an influence on the position, on blocking the position for metabolism. SAR, the electronic effect, the electron withdrawing nature of the chlorine atom can influence the electronic distribution in the molecule, affecting receptor, just the way we have seen that halogens are electron withdrawers. And once they withdraw electrons, they will affect the distribution of the electrons within the whole molecule, and therefore have an influence on the way the molecule bind the receptor. Change the position of the halogen or replacing it with a different substituent can decrease efficacy. So again, remember, when we talk about this substituent, it's not just a substituent being in or any position that it pays up, because as we have said, when those groups are put in whatever position, they influence certain position of the overall molecule. As I have told you, like if you put an amino group are also para director. Means the para position and the other position will have high electron density. When you look at the halogens, they are also para director, and that's why we are saying that it is not only putting a specific the position is also important in the overall reactivity of that molecule. Other different substituents can decrease the efficacy. Electron donating or electron withdrawing groups, general electron withdrawing groups such as chlorine and the para positions are more favorable for activity. Already mentioned that. Modificability, the integrity of the oxazolone ring is crucial for maintaining activity. Any modification that disrupts the ring structure typically results in loss of activity. So that ring is important. This is the one we are calling the oxazolone ring. It is very important for activity. Amide functionality, the oxazolone ring contains an amide functional group that again is also important. Amino group, an amide group. I say that they can of molecules and they can interact usually with the receptor through hydrogen bonds. So again, we are saying these are important groups. They are good, the best to give us the best muscle relaxant activity. So we are only qualifying that structure. We are only saying that this structure of this compound should remain the way it is. Should remain honorable is the best structure that gives you the best activity. Overall lipophilicity, the BB penetration, the molecule needs to be sufficient that it reduces the lipophilicity, can lead to decrease in CNS activity, and that reduce muscle relaxant activity. Let us remember that the receptors for these needs to be such that it has good lipid solubility to allow us this molecule to penetrate in the brain. So when you look at this SAR, it is just telling us that the structure of this compound should remain the way it is for this compound to have maximum of prosoprazole result in inferior, like the non-steroidal, we start with indomethacin. And we say you can change the structure. You can change the indole ring to an Indian ring, into an Indian ring with retention of activity. So we are only saying here, when we look at this molecule, the benzazone, cloxazone was found to have the best activity. And it looks like that structure is the optimal structure for activity. We are not able to change it. Any change of that structure, we have talked about the benzene ring, the flat, the prana, we've talked about the amide, we have talked about all those groups and their importance in bringing the muscle relaxant activity. So we've already said that centrally active muscle relaxant with sedative properties, attacked by blocking nerve impulses or pain sensations. We've already mentioned how these compounds used as skeletal muscle relaxant for reduction of painful muscle spasms and acute or chronic back pain, so on. So these I think we have mentioned. Most frequent side effects: drowsiness, dizziness, nausea, vomiting, heartburn, constipation, and diarrhea. Those are some of the pharmacology. So that now is the other class. So we are moving on well. And as I said, with this one, with the benzazoles, we have only one, the cloxazone. And we are saying that is the optimal structure. We cannot at all change that structure. If we change it, then we'll have a negative influence on the activity. Then we have the heterocyclics or the benzodiazepines. And when you look at the benzodiazepines, again, we call them the benzodiazepines. This is the benzo there in a ring, and the nitrogens. 2 nitrogen is the one we are putting di. Then the ring, the 7-membered ring, is called an azepine ring. So I have explained benzo. That we are not even considering this one. This is a benzodiazepine ring. This is a benzo, benzene, and then the diazepine ring is that we have that nitrogen, and then the azepine ring. The azepine ring is these 7. You can see 1, 2, 3, 4, 5, 6, 7. That 7-membered ring is a 7-membered ring containing 1 nitrogen as a heteroatom. That's the azepine ring. So when you put a second nitrogen, now you call it diazepine. So the benzodiazepine is that structure. And that benzodiazepine, for it to be called the benzodiazepine, definitely it must have that ring. That ring, the basic ring, your ring, that one, the basic ring. It doesn't have to have the 2 nitrogens. It can have, yeah. So it follows then it will be a benzodiazepine. So it will be a benzodiazepine, it must be that structure. But now for these drugs to have, the benzodiazepines to have activity, you find that the benzodiazepine, if you just have this structure there, the diazepine ring, or the benzodiazepine here, which you call position 1, position 2, position 3, position 4, position 5. At position 5 of all the benzodiazepines, you will always find a phenyl ring. At position 5 of all the benzodiazepines, for them to, you can find a substituent at that position, or that position is the same, can have a fluorine group, you can have a chloro group at that position. Most commonly, have a 2, 3, 4, 5, 6, 7 have an electron of the chloro group. That is acceptable. But you do require an electron withdrawing group. This phenyl ring, which we have mentioned in the benzo, also very important. Sometimes it can be substituted by other groups, like the isocyanates, with due retention of activity. But when you have a nitrogen, when you have a methyl group, the resultant compound has much higher activity. For most of the benzodiazepines, and not all, a carbonyl group, which is also a carbonyl group at that position, also is important to give us activity. But not all the benzodiazepines have a carbonyl group at that position. But those which have a carbonyl group at that position, it is necessary. Nitrogen must also be there, nitrogen 1, nitrogen 2, and not all benzodiazepines have an imine group or this double bond there, but it is when you have the double bond, it should be in that position for activity. So those are some of the structural features. It's unfortunate that you haven't done this other unit, but I've mentioned them for you to understand why those groups are there. Again, we have said at this position, having a methyl group increases activity because the methyl group is responsible for binding, or increases lipid solubility and allows that compound to have better lipophilicity to penetrate the membranes. But also you find that this position 1 and 2, the 1 and 2 can also be incorporated in another heterocyclic ring, position 1, 2, of the benzodiazepine ring with retention of activity. So when we look at the next benzodiazepine, which is our plasram, you can see here in this one a part of this ring here, and that ring there, we call it a triazole. You can see triazole ring because it has that. We can also have addition of another ring, that position 1 and 2 of the benzodiazepine can be part or incorporated in a triazole ring with increase of CNS. Benzodiazepine, you can see that ring, and that ring all fused together were found to have much higher lipid solubility, and indeed they were found to have better activity, just CNS activity, compared to the other benzodiazepines. So we are also saying you can have that ring, and when you will also see the imidazole. And the imidazole, so imidazole here is a carbon, so that you can get the imidazole, called the imidazole. Come to name the imidazole ring, you give this position 1, position 2, position 3, position 4. So you call these benzodiazepines 1, 2, 4 trazolo benzodiazepines. So I hope you can remember that. You say 1, 2, 3, its own independently. So you call them 1, 2, 4 triazolo benzodiazepine. And the way you do so is because you can have one nitrogen there, you can have another nitrogen there, and the other nitrogen, you could remove the double bond, and the other nitrogen could be there. So you can also have 1, 2, 3. You can be able to give a specific position of the nitrogen. So we call them 1, 2, 4 trazolo benzodiazepine. But now when we come to number, I've talked about numbering the triazole ring, but there is also numbering the benzodiazepine. We give that position 1, we give this position 2, we give that position 3. We give that. Remember, we always omit the intersection. We give that position 4. So that is how we number the heterocyclic, the heterocyclic benzodiazepine, the heterocyclic ring. We number it on its own, starting with 1, 2, 1. But when you come to number the benzodiazepine itself, unlike this, when we come to number the triazole of benzodiazepines, that goes 4. So in the tetracyclic benzodiazepine, the position 7 denotes that difference. So that is our prazolam. And if you look at our prazolam also, of importance is to note that methyl group at that position. That methyl group gives that characteristic, as we keep saying, that group is joined to an aromatic ring and therefore very highly susceptible to metabolism, giving that compound slightly short. The Pharm again at position number 1, unlike diazepam, the methyl group has been replaced with a hydrogen, and therefore hydrogen. Position number 3 of lorazepam has a hydroxyl group. That hydroxyl group at position 3 of lorazepam increases the water solubility, the hydrophilicity, decreases the lipid solubility. So indeed, if you have to compare lorazepam lipid water partition coefficient, indeed, because it is metabolized to many of its metabolites, you have first of all removed that. And when you remove that, you get the metabolizer of diazepam still active. So you find diazepam has a very long duration of activity compared to lorazepam because it has a longer route of metabolism. It has several routes of metabolism. The first one is removal of the methyl group to give us no diazepam. Then the next 450 of position number 3 to give us again the oxide. So diazepam has a very, very long duration of activity. If you compare it with lorazepam, it doesn't have any of that group. That position is not going to be metabolized. When you give this drug, it will go directly into conjugation. So lorazepam compared to diazepam will have a short. Also, when we look at, we have already mentioned our plasma duration of action. It is metabolized fast to the alcohol. Again, remember I told you there. And unfortunately, that CH2OH formed there is rapidly conjugated by glucuronide, glucuronic acid to give glucuronide to have and kind of an intermediate of action. This also have a intermediate, and these are expected to have a short duration of action. So again, when you look at these drugs, when you look at this dependent on their roots, the duration of activity is mainly dependent on their redistribution, and that is dependent on their lipid solubility. Group here, the color group there, you expect it to have a very long duration of activity, but it doesn't. Because if it's rapidly metabolized, or it's metabolized of activity, kindly differentiate those two that form barbiturate because of the redistribution of the barbiturate. For the benzodiazepines, their duration of activity is dependent on the metabolism into along also some activity. And even the metabolite can be further metabolized to another metabolite, which also has activity, as we have looked at benzodiazepines. For those who have covered that, the unit of the kind of to make you understand that that these compounds, just like all the other nitrogen, you have to have that one carbonic one for benzodiazepines, two on that carbonyl group. Those that contain acid, they are those which do not have that group because they are heterocyclic. That's what I'm saying. For the ones with that group there, it is necessary, it is important for the activity. But of course, we have said it can be replaced as in the heterocyclic benzodiazepines with retention of activity. So those are the three main benzodiazepines which are used as muscle relaxants. And as you continue on, you see benzodiazepines can be used as muscle relaxants. They can be used as sedative hypnotics. They can be used as an anticonvulsant. Many subunits, that's alpha, beta, gamma subunits. And therefore bring about the different activity, biological activity, sedative hypnotic activity. The receptor is very complex. Alpha subunits, about 3 meters. Then you find that those subunits. And once it binds the several subunits, it can bring about different activity. It can bring muscle relaxant, and it can also bring the sedative hypnotic activity because of lack of selectivity. There is lack of selectivity in the binding of the benzodiazepine on the gamma butyric several. You can have several, and that, remember, they are binding on the thing, the inhibitory activity of GABA, and once they do so, they will bring an decrease in the muscle tone. They will bring and depression of the at the gamma aminobutyric acid. They will also act at the GABA synapses, and once they act at the GABA synapse again of any origin, they also cause sedation. And one as the general SAR, I will not go surely into details about it because I've already explained. And again, as I have said, you're going to do it in details when you discuss the benzodiazepines, sedative hypnotics. But what I've told you is just what is here. We start at that position, a hydrogen activity, and you can have a 2-carbonyl group is important for activity, but it's only triazorin. It should be not triazole. Triazorin or imidazorin increases activity, as we've already said. Then substitution with a 3-hydroxyl group at this position will benefit glucuronide and therefore decrease in duration of action. Without 3-hydroxyl group, the pin will have a longer duration. Cause also of importance to know the group at that position. It means it does not require to be metabolized to bring about the functional group, and therefore benzodiazepines, the hydroxyl group at that position, you expect them to have lesser drug interaction, even if they are given with their metabolism. If they already have the hydroxyl group, they do not require the cytochrome P450 enzyme to add a hydroxyl group there. So benzodiazepines like lorazepam to the phase 2 metabolic process, and therefore they will have lesser drug interactions with when given concomitant to the cytochrome P450 enzyme. So that's another drug interactions when given with other drugs that require the cytochrome P450. So that is position number 3. This imine group at position, the double bond at position number 4 increases activity. 2 or 2 prime, 6 prime substituted with electron withdrawing group also increases activity. So that is a 5. And if it's substituted at position 2 or position 6, as we have already said, we also increase activity. We decrease activity. Then we have mentioned, and the higher the electronegativity of that group, the higher the CNS activity. But it was found when now you talk about the heterocyclic benzodiazepines, they really do not require a 7 electron withdrawing group for activity, but it is there, but it is not a requirement. But for the other benzodiazepines, which are not heterocyclic, this is a must. I have said it can be a nitro group, it can be a chloro group, it can be like when it's a nitro group in the nitrobenzodiazepines, you find that they are more potent, but we don't have any of them as a muscle relaxant. I don't have an example. So just note, you require that group there. Change of that group will result in a decrease in activity. The higher the electronegativity, the higher the activity. So these are just, it's a very good summary. The effects of ring A on activity, aromatic ring higher than heterocyclic and heteroaromatic ring. So again, the phenyl ring, which is the phenyl ring, that's ABC ring. The phenyl ring again is important for tears, like the thiophene ring. The furan ring are isosteric to the phenyl ring, but there will be a decrease in the CNS activity. So specifically, and of course, when you have a decrease in the CNS activity, that means there will be also a decrease in the muscle relaxation. One nitrogenous group instituted again like diazepam, which has a methyl group there, it will have higher activity than no diazepam. One, because that methyl group is important for, of course, increasing. Indeed, as a summary, if you could just remember those points as a summary of the benzodiazepine SAR, then you are good to go. Because again, as I have said, you will discuss the benzodiazepines in details under CNS 2 because the benzodiazepines are very, very good, are very, very, very good. Sedative hypnotics, they have also benzodiazepines, which are very good at conversions, and therefore you have to discuss them again. Mode of action of the benzodiazepines, we have already said, again, not new, just like the others we have discussed about GABA. These drugs produce centrally mediated skeletal muscle relaxation by acting on the benzodiazepine receptors in the midbrain reticular formation and on the limbic system. Act on the benzodiazepine receptor, GABA allosteric receptor. They bind at another receptor, which is an allosteric receptor, but do what GABA does, and therefore potentiate the activity of GABA by increasing chloride influx or chloride movement. And when you increase chloride influx, that is inhibitory in nature. They increase the chloride influx, produce hyperpolarization, decrease the firing rate of the neurons, inhibit also the calcium-dependent release of the neurotransmitters. This is also something we have also discussed when we were, discussing, I think we were discussing the benzodiazepines. It is only that these two drugs bind their own allosteric site. They don't bind the same site as GABA. They do not bind each of them. Benzodiazepines and barbiturates each bind their own allosteric site, but their mode of action is very, very similar. So again, that there we are happy because we have also discussed the barbiturates, which have a very similar mode of action. The major difference is that the barbiturates are said to the chloride channel, they increase the duration, whereas the of the opening. Barbiturate increase the duration of opening, the benzo, each of them in their own way, increase the inhibitory activity of GABA, and hence will by the cytochrome P450 enzyme, that is phase 1, then conjugated with glucuronic acid or glucuronic acid, which is phase 2, and then and we have said when we look at diazepam, I've already mentioned oxidative and dealkylation, very, very important. Catalyzed by, then again, against you catalyze pumps, and then once you get the oxazepam, then the oxazepam can be very say that methyl group and going oxidative hydroxylation to the methyl undergoing conjugation very rapidly. Again, very rapid, removed from the body. When you talk about lorazepam, it already has the hydroxyl group, so readily conjugated. So again, the roots of metabolism are dependent on the structure. I have seen Nick calling, so I think and, let's stop there. All right. Nimeenda sikuona. Hope hamkutoka. Sawa. I normally, even if you write it here in the public chat, on the other side, you don't see the pub. When you enlarge, when you increase the size, you don't see the public chat. So not unless you something. All right, but we are doing well. Najua mliniambia to continue, so we continue. But if there's anything you have not, once we finish the break, go to the last, which is the CNS stimulants and the hallucinogens, and we'll have finished. So as I very much, I hope most of you stayed with me. But as I, and we'll start from there. Thank you.